We are going to talk today about performance best practices. I am Scott Drummins. I have worked for VMware for about 3.5 years, at which point I was expelled all the way across the Pacific. No, actually I was not. I did choose to go and pursue a life in the exotic Far East with EMC's vSpecialist program. However, when this talk was submitted, I was still a VMware employee and had worked with my mostly good friend and sometimes enemy, Kaushik Banerjee, on submitting and creating this content. So for the purposes of today, I did this funny strikeout just to let everyone know I'm really presenting as a VMware performance person today. There will be no EMC sales pitch at any point in this talk. Yeah!
Oh, wow. All right. EMC sales pitches are popular, it looks like.
I know.
So I'm Kaushik Banerjee, as Scott mentioned, and I run outbound performance at R&D in VMware. As part of my role, I produce a lot of the performance collateral that you see out there for VMware. Not all of it is produced by my team. Some of it comes from the rest of the performance engineering teams that we have. It goes through my team and becomes consumable. So among my jobs, I work with partners to enable their performance collateral, and as well as deal with performance escalations that come through our support organization and finally come to us. So let's quickly go to the agenda here. We will talk through a little bit of the ESX architecture overview. Most of you are familiar with it. We will try and hit the points that need a little bit more explanation. We won't dwell on it too long. And then, based on our experience with dealing with various partner performance issues, various customer performance issues, we'll hit certain areas of the product. As you are all well aware, the volume of subjects in the ESX performance domain is pretty large. It will probably fill up a day or two. So we cannot cover everything. So we choose a couple areas that we want to hit well. So storage and memory are the ones we have picked up for this talk. We'll talk a little bit about new features that we have in 4.1 that might help you in your performance journey, and give a few little performance troubleshooting tips. Now, in the previous talk that we did, this is a repeat session, I had pointed to other talks that you could attend where you could get more information on getting some of those detailed troubleshooting tips. Obviously, we don't have that opportunity on Thursday afternoon, but you could consult recordings of those talks. We'll also point to some documentation that might be helpful in this area.
So I'm going to start off with the slide I use in every one of my decks to give everyone a little bit of a feel for how to talk like an engineer like Kaushik and not like a marketing person like myself. But I'll tell you that you are either very lucky or very unlucky in that today we actually have a deck to present. When we gave this talk on Tuesday, I believe it was, the room had 750 seats and they were all full, and there was no deck for the first 25 minutes. Yeah, it actually, though, we did a little bit of Q&A, a little kind of little dance up here, and that worked. So what we're going to try to do is stop a little bit early and make sure that you guys can shout out some questions. And if they're relevant for everyone, which I'm sure they are, because we've gotten great questions so far, we'll cover those. But back to the content. So first off, one of the things I want to be sure everyone understands, and this is key to the way you think about how ESX works, and don't believe the hype. I mean, there's a lot of good products coming out of VMware, but if you are worried about an application's performance, what you're thinking about is ESX and the components it touches, the infrastructure it touches. So when you think about ESX, I want you to start thinking less about ESX as one product and think about it as two distinct components. I learned over the course of probably took me 6 or 12 months to detect this pattern that VMware's engineers were not using the term hypervisor very much. And in fact, it's kind of rare that you ever hear engineers, except in public-facing discussions when they're talking to customers, ever use the term hypervisor. What they're much more comfortable using are the terms monitor and kernel. And these are two components that are dropped together to make what you know of as the hypervisor. Now, the monitor provides the thin level of presentation to the guest operating system to make it look like the virtual machine is communicating with hardware. Of course, there may not be that same hardware present. In fact, who knows what is running underneath. That's just an abstraction layer. Now, VMware's monitor runs in 3 different modes. So VMware calls it, obviously, a multi-mode monitor. The three modes are binary translation, which means full software virtualization. This is what VMware has been doing for ages. Second, hardware assist. Hardware assist means leverage new technologies that have come out of Intel and AMD to make virtualization faster. And third is para-virtualization. Now, I actually want to give you one more word on each of these technologies. Hardware assist, actually there are two flavors of hardware assist, or two phases of hardware assist. The first came out around 2006 or so, where Intel and AMD produced support for privileged instruction execution in technologies called Intel VT and AMD V. But later, much more recently, 2 years ago for AMD and last year for Intel, they also added memory management virtualization. So this means all of the virtual memory management has been pushed down to the CPU. And this corrected the performance of a class of applications that VMware calls MMU intensive, memory management unit intensive. Number one workload there, Citrix. Citrix presentation server, aka Citrix XenApp. Number one MMU intensive workload. It's a terminal services workload. Very, very MMU intensive. Always run that on a newer hardware memory assist system. The second, it just came up in the group discussion I did, was a gentleman said he was running a Unix script that was looping and forking off processes, and he noticed it was performing so much better on Red Hat's Zen, which has a full paravert guest, than it was on VMware vSphere. He was running that in an Intel part, a 7400, that did not have this MMU. So you should upgrade to Intel 5500s or better to get that feature. The last comment I'll make about the monitor mode is paravert. Paravert, if I'm to generalize, I can say paravert is dead. Paravert is no longer needed. Paravert was very important for a period of time that hardware assist wasn't yet there, and that we wanted to avoid some of the overheads in mission-critical applications. But now hardware assist is so fast, the gains you get from paravert are zero for all practical purposes. Now, when I say paravert, what am I talking about? I mean para-virtualized operating systems. Operating systems that have been recompiled to communicate directly with the hypervisor. That technology is no longer needed. What still remains viable and very, very useful is para-virtualized device drivers that fit into the supported, compiled, common operating systems that you're using today. VMware provides para-virtualized device drivers for storage. It's a vSCSI adapter, PVSCSI, as well as network, VMXNet, and some others that are a little less important, like SVGA. Now, that's just the monitor. All that is just this thin presentation level. Beneath that is the kernel, and this is really the operating system of ESX. It does all the things OSs do. It schedules, it allocates memory, it provides the virtual storage stack and the virtual network stack. We're going to talk about in detail some features in the network, storage, and memory. But I will mention that it's funny to me as I engage customers over the years how much the performance problems have changed. We used to be very hypervisor-centric in our type of analyses. For instance, people would come to us with questions about high ready time and SMP and want to know what they could do to the scheduler or VM sizing to correct things. I'll say for the most part, not entirely, but for the most part, those issues about hypervisor changes, of really kernel changes, are not as relevant. What is much more important today is actually worrying about what the underlying platform is doing and how you're communicating with it. So how do we determine what workloads you can run? Well, the simple way is just to look at the four basic resources and ask ourselves, where are the ceilings of VMware's performance, of vSphere's performance? First and easiest is CPU. Okay, on the far left is spec CPU. Just test CPU performance. And you can see the blue line native and the red line are very, very close. This basically means that for CPU-intensive workloads, vSphere delivers about the same performance as native. Next is memory. Well, I mentioned that memory was a real issue. This was first corrected by AMD and RVI. That was supported in ESX 3.5. And later last year, Intel's EPT was supported in vSphere. What about network? Well, VMware's been doing wire speed, has demonstrated wire speed network throughput running to the full 10 gig link, so that's not your issue either. How about storage? Well, last year, using some SSD disks, VMware was able to demonstrate 365,000 IOPS in a single host. And if you don't know what an IOP is, let me put that in perspective. If that was an Exchange mailbox, that would be the equivalent of 700,000 Exchange mailboxes on a single physical host. So this is I/O so far in excess of what people need as to absolutely eliminate I/O as being a problem for performance issues. So here we are. We're looking now at limits that are fantastic. The hypervisor has become transparent in terms of its limits. It's basically a pane of glass that's projecting through the rest of your infrastructure. So we ask this: where are the performance problems coming from?
So a lot of the problems that we see today come from misconfigurations. And a lot of these misconfigurations that we see are in the areas of storage. So in this presentation, we'll actually go into a little bit of how basic storage is configured, whether it be physical or native, and then get into what difference does it make when you configure storage for virtual environments. So how do you configure storage? Well, you have applications that run on, let's say you're doing it on physical server. You have a physical server, you have an operating system, you have an application running on top of it. Simplest case. Now your application will have a certain demand in terms of capacity. It will have a certain demand in terms of IOPS. And you'll meet these demands in terms of both of these criteria by configuring a certain type and number of spindles. And it's not just the spindles. It also depends on how you configure those spindles. So it'll depend on the type of RAID you choose. So if you do RAID 0, it gives you no protection, but it gives you full throughput from all those disks. If you use RAID 5 or RAID 6, you lose some throughput. You'll give up some for your parity disks. Your writes, if they're not being satisfied from your array cache, may suffer a little bit on the write throughput that you have. But that's kind of where it is. If you're using RAID 1.0, then you're getting half the capacity. You're probably getting the same read throughput that you can get from all those disks that you're allocating to the LUN. Your write throughput may be lower. So once again, it depends on the SAN cache, right? The other thing that determines this is the type of spindles you have. So if you have the older 5400 or 7200 RPM drives, then you can do a smaller number of IOPS per disk, maybe about 75 before your disk starts slowing down. And if you're faster disks, 10K or 15K, you're approximately doubling maybe the number of IOPS you can do. If you go to the latest SSDs, then you can do much, much more, an order of magnitude or more IOs per disk. So great. So this is kind of the baseline of how you do stuff for storage. So what happens when you virtualize this? Nothing really changes. Your disks are still capable of the same amounts. You'll configure your LUNs kind of similarly. The only thing is that now you don't have a single application running on a host. So very likely you now have a single server that has many application instances running on multiple OS instances. And since you cannot really allocate a LUN per application anymore, you'll probably create VMFS and have many of those applications going to these LUNs. And this consolidation can have certain effects, and that's what we want to talk about.
So we would like nothing more than to be able to tell you that you just do the exact same thing you're doing in your physical environment and everything's going to be fine. And that is a very good generalization of this problem, because what's funny to me is how many times we talk to VI admins who ask us a question that on the surface seems like a good question, but when you think about it is not practical for the solution. They say, what is the best storage configuration for a virtual environment? Well, a virtual environment, as Kaushik points out, doesn't really change the sizing at all. It's just, think of it as a container now for all these applications. What you're really sizing for is for the individual applications themselves. So just follow those best practices and you're done, right? It's not quite that simple, okay? You have a choice to make. There's a sliding scale among how much consolidation you're going to do in the storage space. One is you're going to have, at one end of the extreme, one workload is given its own LUN. And in another end of the extreme, you're going to put a whole bunch of workloads all sharing one LUN. Well, what are the differences between these? Let's look at the one case first. People used to believe, in fact, many of you may still believe today, that RDMs are better performing than VMFS. May I ask, honestly, how many of you still believe that RDMs can beat VMFS in a drag race? Few? No brave souls. Good, we're talking to the right audience. I'm not going to look anymore. I thought I saw one hand, but I'm going to ignore it. Okay, so that message is out there a little more than we'd like to believe. And the truth is that if you test apples-to-apples configuration, one VMDK on a LUN versus RDM, as this shows, there's very, very little performance difference. There are some cases where you can highlight slight difference with what I consider not terribly realistic workloads. However, there is something else happening with RDMs that actually makes that configuration potentially more attractive in some environments. Consider this. For ESX in the VM kernel, one device queue is instantiated for each LUN at each HBA. This means if I have one HBA and it's communicating with 5 LUNs, there are 5 device queues. If I have 10 VMs are all going to one LUN, they are all sharing the same device queue. Now, for the purposes of queuing, when I go forward in this presentation, we're just going to talk about a fiber channel queue, which is defaults to size 32. So this means that in some environments where people are comparing virtual to physical or virtual to RDM, what they're really comparing is queue sharing to queue isolation. And queue isolation can be a little bit faster. In some environments where workloads all come up together and demand from the same LUN at the same time, the queue will overflow, and that will, of course, increase service times. But that's not because RDM is faster. It was an artifact of the sizing. Now, what happens when we consolidate? There's 2 things to think about. I already mentioned queues, but I want to point this out.
So, Scott, just before we get there.
Please.
So if you go back to the previous slide, one thing we want to point out here, though, is that there's a cost to having that individual queue with RDM. It means that each application now has one RDM. Imagine a situation where each server has 8, 10 applications running. You have a server farm that has 20, 30 servers maybe. So you're talking 200 or 300 LUNs to manage. It quickly gets to be a pain. So VMFS gives you something for that device queuing that you see there. And it's a cost that we choose to pay, the same way that we choose to run multiple applications on a server, because it's just not worth having that many. So you have to keep that in mind. You get something for giving up that isolation.
So let's look at what happens when you consolidate multiple workloads. This was done by VMware a couple of years ago in response to some claims that showed up in the industry about poor VMFS scalability. So what VMware did was they set up a chassis of many blades. There were a total of, I don't even know how many chassis were involved, but 64 blades of, I believe it was an HP system, if I'm not mistaken, all driving load to one VMFS volume that had many VMDKs. And they tried 4 configurations, random I/O and sequential I/O, each doing either all read or all write. And showed as you add more and more hosts all going to the same volume that performance was steady, right? Performance did not drop. Aggregate throughput did not suffer as the result of more VMDKs being placed or more I/O going to a LUN. Why is this? Well, you'll hear a lot people talk about SCSI reservations or locking contention in VMFS volumes. But it's important to know that locking only happens in the presence of administrative operations. During normal I/O, there is no locking at all. So scalability is perfect. But I will draw your attention to that one line that's falling there. The sequential read performance starts at sequential performance and ends at random performance. Why is that? Well, what happens is when multiple sequential streams all end up at the array, they get interleaved. And it looks to the array as it processes those I/Os as if it's random I/O. So what starts at sequential performance ends at random performance. Now, why do we bring this up? Another question that we're always asked, I said earlier that someone asked me how they size for a virtual environment. One of my responses is because consolidation is changing the profile of your storage workloads, it is impossible for you to know in advance what your storage profile is going to look like until you consolidate. So you have to design an infrastructure that's flexible. You have to consider having, say, 3 tiers of LUN performance on your array. One has got many spindles. Maybe it's RAID 10 or RAID 1+0, as a storage purist may say. Maybe one is 5 with more spindles, and 4 is some third one is some cheap SATA configuration. You can move in between these with storage vMotion non-disruptively by paying attention to the queues and the latencies that we're going to introduce shortly. Which queues are these? Well, I mentioned that there is one device queue for each LUN at each HBA. Anytime that you overflow this queue, commands are backed up into the kernel queue. And you can think of that kernel queue as being infinite. Of course, nothing is infinite in software. But it is enough to hold a substantial amount of backup. So anytime that you have queuing into the kernel, that is a sign that something is going wrong. Commands should pass through the kernel like greased lightning. Nothing should be obstructing them at all. As soon as they hit a full queue and they have to wait in the kernel, some action is required. Well, usually what does that mean? Most of the time it's because the array is slow, there's something going on with the storage configuration, it's not servicing IOs fast enough. By correcting that, it will drain the device queue faster, and that means things will come off the kernel queue. Very, very rarely you need to make some modification to the ESX device queues, but that is a last resort, not a first. So now, we haven't really given you answers, but we've given you some food for thought. On one end of the spectrum, we have one-to-one mapping, hopefully not with RDMs, but possibly you want to put one VMDK on VMFS. And on the other end of the spectrum, you want to have many VMDKs all placed on a single volume. What is the difference between these? Well, think about this. If an ESX host is connected to 10 different LUNs all in the same array, and each of those LUNs gets its own HBA queue, each being driven by a VM, if all of those VMs wake up at once and demand I/O out of the array, that's 320 commands going to the array at one time. That is an intense burst of I/O. Is that something you want? Maybe. Really depends on your environment, right? Your storage admin might not want it, but it's possible that your application owners are expecting that. So you might favor a configuration that would support these very intense bursts coming off of one host. Maybe the opposite is true. Maybe these are not workloads that you think should be able to demand instantaneously so much from the array. In that case, high consolidation and sharing queues is very efficient, very simple for management, and it will level out those IOs through the queue size over time.
So a couple other things that come up in the storage space. Also, the one thing that I want to mention before I get into this, there is a people problem here too. It's how application owners interact with system administrators and storage admins in a physical world, and how they interact in the virtual world. Sometimes this interaction kind of goes application owner to VI admin or VMware admin, and then it kind of stops there. And we can't that's really not the way. If you have an IO-intensive application, then it's very important that it still remains a collaboration between the storage, the VMware administrator, and the application owner. So it's kind of a non-technical answer to the storage problem. So a couple other things, VMDK lazy zeroing. So this is another thing that you may have encountered, and we encounter it a lot because we deal with proof of concepts and benchmarking scenarios. It doesn't come up that much in production. And what is this? So by default, when you create a VMDK, a volume for your a storage volume for your VMware for your virtual machine, VMware we do not zero out that volume. So what we'll do is we say, you need 2 gigs of space, here's the 2 gigs of space, and boom, we are done. Except when you go to write to it, we make sure that we write zeros to that block before we allow the VM to use that block. Why do we do that? A VM should not release some space, and then some other VM should not be able to allocate the space and be able to read off of it. It's a security thing. So we say, great, so we have to zero it. What does that mean? It means if you're using a block for the first time, it's not been written to yet, you're effectively writing to it twice. You're writing zeros to it first, then you're writing the actual data to it. What happens if you read that block? It's not been initialized yet. Now, in the file system header, we know that that's supposed to be zeros, but we have an optimization. If you try to read it, we don't go and write the zeros and then say, hey, here's the zeros. From the file system header, we basically go, that's supposed to be zeros. We haven't zeroed it yet, but we know they are zeros. We don't need to read it. We just return the zeros. Now, in a benchmark scenario, that does 2 things. If you do a read test on an initialized volume, we are much faster than native. And, this is awesome, right? Nothing, you should never believe a benchmark that says this is faster than native unless there are very clear, unless it's been analyzed to depth and really understood as to why that's happening.
And in no way is he disparaging the presentation I gave called Faster Than Native.
Yeah, because I vetted each one of those, and those are actual true cases where we are indeed faster than native, and it's been carefully analyzed to understand why those situations happen. But if somebody casually comes up and says, I ran this test and it's 3x of better than native, no. You have software, you have an operating system, you have a hypervisor, and eliminating the hypervisor makes it fast. Somehow it makes it slower, and inserting it makes it faster. There's something wrong there. So you got to take that with a grain of salt. So a read test on an initialized will come back very fast because you're not going to the disks at all, and B will give you a lot of zeros really fast. Whereas if you're doing writes, we are doing 2 writes. So effectively, somebody might come and say, this thing sucks because I'm doing a write test and it's really, really slow. Yeah, it's slow the first time, but look at your production applications. If you're creating an Exchange database, if you're creating an Oracle database, either way, you'll initialize your space before you start giving it to your users. How many writes do you do to how many reads do you do? On a piece of data, the ratio is somewhere between 25 or 100 or 1,000 to 1. You read that data many, many more times than you write to it. So, well, write to it the first time. You might do updates to it. So, effectively, what that means is in a benchmark scenario, you might see these strange situations. It's not likely to happen in production. Oh, the one thing that I missed here. So, zeroing has a cost, and we are trying to offload that cost from the server to the array vendors, to the arrays. And the arrays can do it in hardware much more efficiently. So we now have a vStorage API for array integration, VAAI.
First time he's gotten it right yet.
I know. That we call it VAI all the time, and when I have to say the full thing, oh boy, that's a mouthful.
I told him engineers are not responsible for getting the terminology exactly right, but I'm very impressed with that.
And you know, marketing changes it on you for 3 or 4 times, so just to keep you on your toes. So VAI, from now on, I'll never refer to the whole thing anymore, okay? So what does VAI do? Zero offloading. What that means is instead of actually writing the zeros from our side, we tell the array that from this block to this block, can you make them zeros? And it does it. So it happens in the array much more efficient.
And it's worth noting that some arrays actually don't need to write the zeros at all. They can just maintain an internal map, and when they're told to write out all these zeros, say, yeah, I got it, and just return zeros from memory eventually. From
so now instead of us returning the zeros, they return the zeros.
I don't know. I'm sure lots of vendors do that. I wouldn't know any that do.
Good question. All right. So the next one, thin provisioning. So this is something that we introduced in vSphere. And what this means is when you allocate space for a VM, you can say instead of allocating all of the space, just give me a minimal amount now. And as and when I actually use it, you can allocate more. So you're allocating 8 gigs of storage for the VM. You get a certain partial amount. And then as and when you start writing to it, the thing will have to grow so you can your VM actually gets the space. Now, what does that mean? Scott mentioned earlier that we have to log the array for administrative operations. Well, growing this space is not a LUN. And growing the VMDK as and when you run out of space is an administrative operation. What that means is if there are 2 VMs on 2 separate hosts, they both say, I need to grow my VMDKs, they shouldn't be able to go grab the same space. You have to manage somehow that control so you get locks, basically, right? So this operation, we believe, we have to go lock the array. No, you don't really lock the array. You lock it for a specific operation. It allocates the space, and then it quickly releases it. It's not locked through that space being allocated, etc. So it's very efficient. And as you can see, the impact of the actual growing these graphs, so where you have a graph that shows thin post-zeroing, it's at a certain level. Thin zeroing is at a much lower level, right? So the impact of the locking is very, very minor compared to the impact that the zeroing has. The zeroing is still doubling the amount of writes that you do. The locking is a one-time operation for the growth. So it has a very minimal impact. So once again, VAI has an option here. So array vendors are implementing ATS, which allow that locking to pass to the array and be not done at the server level, which is great. But in general, thin provisioning, you shouldn't have too many concerns on the locking side on thin provisioning. All right. So the next couple of things are new features in 4.1. And the first one is SIOC.
So SIOC, as I learned from the group discussion I just led, is probably the performance feature people are most excited about in vSphere 4.1. And it corrects a very confusing feature that existed in 4.0, which is that in 4.0, all storage resource management was done at the host level. It was not cluster aware. What this meant is if you ever went in and played around with shares in 4.0 for storage shares, that it was only enforcing those for the VMs that were co-resident on that host. What does that mean? Well, let me give you this one example here. Let's pretend that the ESX server on the left has 2 VMs. One of them has many shares, 1,500, and the other has few, 500, because one is 3 times more important. And there's a third VM, VMC, that is also unimportant, only 500 shares on a distant host. They're all sharing access to the same VMDK, and then the same VMFS volume. And then in the presence of contention, they all wake up and demand more access to the storage than is available. What happens? Well, each ESX host arbitrates access to the queue, meaning that on the host on the left, VMA does well. However, on the host on the right, VMC is given full access. Now recall the queuing I mentioned before. That queue has been simplified there, but it means it can open 32 commands to that LUN. And VMA is only getting a fraction of its 32-element queue. This is not the correct prioritized access we want to see to a volume. SIOC does something that is actually fairly simple in concept and is elegant in implementation, which is it monitors latency at the volume level, and when latency crosses a certain threshold, it then doles out IOs to the higher priority VMs across all VMs in the cluster. So now that storage resource controls are maintained by VC, and the calculations are done exactly like CPU and memory. Now, I think SIOC is absolutely fantastic. I think it's a wonderful product. I think that you guys are all going to get a lot of use out of it. I always caution everyone with just a few words of wisdom. The first is it's not a storage panacea. If your storage was screwed up before SIOC, it is still screwed up with SIOC. So don't put too much faith in it. The next is it kind of trades throughput for latency. By doling out these IOs to the VMs that deserve it, that you have determined are your most important, it will make sure that the latency stays below a certain threshold. And as a result, the average throughput might go down some. But again, that's in the interest of protecting your most important VMs. And finally, just a little slight warning. Now, you remember the example where VMC was fat, dumb, and happy by itself on a host, monopolizing your array and getting more access than its than its shares said it was worth. The day you enable SIOC is the day that guy has to start being a good neighbor. Now, that's great for you as an admin. It's great for the majority of people on the infrastructure. It's not so great for that one app owner. So he may be a bit surprised. Again, SIOC is wonderful. Everyone should go out and play with it. I believe that Kaushik has found through experimentation recently that there's a feature he likes even more.
And a related feature, at least in terms of name, similarly introduced in 4.1, is network I/O control. And what does network I/O control do, and why is it important? So the networking infrastructure in general is going through inflection. You are going to introduce 10 Gbps, whether it's this year, whether it's next year, it's coming. But what does that mean? Currently, your servers probably have many network ports. You have 4, you can put a couple quad-port cards, 8 network ports, fairly cheap. However, once you go to 10 Gbps, that's no longer an option. First of all, each of those adapters costs a lot of money. The ports on the other end, the switch ports, cost a lot of money, and they draw a lot of power. So effectively what that means is, and it's kind of difficult to go to the bean counter and say, hey, I want 80 Gbps of output from my server. Why do you need 8 10 Gbps ports? Makes no sense. So you'll end up with maybe 2 10 Gbps adapters. Guess what? On a VMware infrastructure, you do a lot with those network ports. Your management traffic goes through those. Your storage traffic might be going through those. Your VM networking goes through those. Your vMotion happens through those. FTO happens through those. So how do you protect all these traffics from one another? How do you make sure that one does not clobber everything else, and suddenly part of your infrastructure starts failing because that piece of the network doesn't get enough throughput? So that's what network I/O control enables. Let me show you an example of that. So here's a test that we did, and we are running a spec web support benchmark. Okay? And we're running 17,500 users, that little number by the blue bar that you can't read. So what is that? It basically means that these are the number of users I'm running, and the red line represents how many are passing the SLA for that action. So a spec web support workload, basically it simulates users downloading patches. They need to get their patches in a certain amount of time for that test to pass. And as you can see, the red line is fairly close to that blue line, and everything is passing happily along, except at some point, a vMotion starts. And what that does is draw out a lot of your network throughput. What that can do is it can suck up enough that your users are no longer getting enough throughput from the network because it's going elsewhere, and some of them are not meeting their SLA requirements anymore. Using vMotion, using network I/O control, what you can do is you can say VM network traffic gets a percentage of your network. So 70% of your throughput is reserved, not exactly reserved, but available to your VM network. So what that does is it allows, in this case, if it were indeed 70%, you would actually be able to reserve 7 Gbps for your VM network. And even through the vMotion, your users would continue to pass the SLA requirements that they have. Now, here's how network I/O control really works. So this is implemented as part of the distributed switch. And there's 2 layers to this. So the first is the shaper, and the shaper is where limits are enforced. So what you could really do is you can say, my VM network, all those VMs over there on the left side, they are allowed to use a certain amount, let's say 5 Gbps. Your management traffic is allowed to use 1 Gbps. Your vMotion is allowed to use 2, and so on, and the sum of all that would make up your network. This is not something that we recommend. And the reason for that is that let's say you have a situation when your VM network traffic is very small. Let's say it's only 500 MB. Do you really want your vMotion constrained to 2 Gbps at that point? No, you want your vMotion to go use everything it can. So that's why what we recommend is that you use shares. And the shares is what's implemented at the scheduler layer that you see over there. And what that does is, let's say you have 50% or 70 shares, for example, for your VM network traffic, and 15 shares for your vMotion. What that means is, if there is contention, if you are oversubscribed on the network link, then yes, 70% will go to the VM networking, and 15% would go to the vMotion. However, if the VM networking traffic is low, then you're still able to use the full capacity of your link. So network I/O control is a great feature once you move to the next generation of network infrastructure.
So I want to talk a little bit about memory, but maybe I will, in the interest of time, give you guys a very, very short summary of memory transparent page sharing. I think we said in the abstract this was an advanced session, so I bet 90% of you get this, and for those of you that don't, it's just dedupe. Next slide. Okay. After that is ballooning. Similarly, advanced session, you guys all get this. What is ballooning? It's taking memory from VMs that aren't using it and lending it to those that most need it. Now let's look at the performance impact of these in a study that I love that was done by someone in performance engineering called Fei Guo about a year ago. He did this analysis of 2 hypothetical hosts, but he did very practical data. One of them is only ballooning, and the other is only swapping. And we're going to do 2 tests across VMs in these configurations. And we're going to limit the virtual machine memory to force either ballooning or swapping. The first test he ran was Linux kernel compile. Kernel compile was placed in a VM, and the VM was limited as we go from left to right, from initially 512 megabytes to a final 128 megabytes. The bars represent how much memory was reclaimed, and those 2 are fairly equal, as they should be. But what's very interesting is the change in performance. The blue line means that the system in which the balloon driver reclaimed up to 75% of the memory, its performance never dropped. However, almost any swapping at all hurt performance. It dropped slowly for sure, but even a 25% reclamation due to swapping was hurting performance. Why is this? Because the guest operating system, when it's asked to inflate the balloon driver, when the balloon driver tries to inflate, can make very smart decisions. The guest operating system has all kinds of classifications of its internal memory. It knows what's kernel memory, it knows what is user memory, it knows what's heap, what's static, it knows what's being used to buffer IOs. So it can make prioritized decisions about which memory can be retired. However, ESX is forced to randomly swap. It has no idea what memory it can pull and which it shouldn't. So when it randomly pulls pages, those very well could affect performance. Now, this is kind of a simple benchmark because kernel compile uses very, very little memory. So it's not the best representation. But let me give you a more realistic curve. This is Oracle Swing Bench. Exact same configuration, okay? We're going to set up Oracle being tested by Swing Bench, an OLTP workload, and we're going to limit all the way down to about 30% of the original VM size. And what happens? Well, again, the balloon driver is very efficient about reclaiming memory. It reclaims all the way into the point where the blue line, it hits some kind of magic number where performance drops off. Now, for those of you that know a lot about databases will recognize this is the point that the balloon driver encroached into Oracle's SGA. And those of you that don't know what databases are, this is really the point where the balloon driver encroached into the important part of memory. There's always degrees of importance in the guest. And when the balloon driver gets big enough, that's when performance hurts. But the interesting message here is that this VM was sized twice as large as needed. And the balloon driver happily reclaimed half that memory without any of the users ever knowing it was happening. The balloon driver is great. As I said in my blog post, you should love your balloon driver. The swap engine, however, is forced to make random page selection. Even a little bit of swap behavior, shown by that cyan line, I guess it is very bad for performance. It drops immediately and unrecoverably. Now, let me show you the final bit. This is Java. Java, look at that. Java is very interesting. Both the balloon driver and the host swap kill memory performance. Now, remember how I said that the balloon driver is so good in most cases because it's inflating through the assistance of the guest operating system. And the guest operating system is making smart decisions about memory management. The guest operating system, when Java is running, doesn't know anything about memory management. It's the JVM that's managing the memory. So the guest operating system is just as dumb in this case as ESX is. So both the host and the guest are making bad decisions when they're trying to reclaim memory. This screams for some sort of a balloon driver aware JVM, and we can only hope we see something like that coming up as soon as possible. The correction for this is not to disable the balloon driver. That is a desperate and overreactive approach to this. All you need to do are set reservations. Pull that reservation limit up to account for the size of the Java cache, which, by the way, is often set on the command line. I hope many of you saw our friend Justin Murray present the Java Best Practices. He always includes this in there. Know what your Java heap size is, set reservations appropriately. This actually also goes for an Oracle SGA. You want to make sure you protect that. When you protect that memory, it will stop both ESX and the balloon driver from encroaching into that memory space.
And the last thing that we'll talk about in the memory compression area is, in the memory area is memory compression. And this is another new feature that we introduced in 4.1. And memory compression may sound like, you run an 8 gigabyte VM, and we compress the memory and it fits in 6.5, and boom, we're done. No, not quite. What this means is we have another layer that can help you with memory over commitment. So we'll try saving memory using transparent page sharing. We'll try saving memory reclaim memory using ballooning. And if even after that we have a shortfall on the system and we need more memory from our memory back from our VMs, then we will implement, then if memory compression is enabled, then we'll try use this to reclaim memory. And what does that do? So you can configure VMs to have a memory compression cache. And basically you have an 8 gig VM, you say, hey, I allocate a 500 meg cache for this memory compression. So what it will do is it will scan the memory of the VM and try to find pages that can be compressed to less than half its size. So if a 4K page, as long as it compresses to less than 2K, it will say, hey, you're a candidate to go into the memory compression cache. It will find 2 of those pages. It will put them on one of the pages on the memory compression cache and free up those 2 pages. So now you're using 1 page instead of 2. If you get better compression, great, you'll get even more. So that's how we will reclaim memory. Now, why do we not do memory compression by default? Because accessing compressed memory obviously is much slower than accessing real memory, because you have to read that memory and compress it before the application can use it. So you don't want to do that unless you actually need it. So, however, reading memory, uncompressing it, is still much, much faster than reading it from disk. So doing a swap in, bringing it in from disk, and then handing it to the application. So this is what you kind of see in this graph. What you see here is that with memory compression turned on, yeah, performance still suffers as you apply more memory pressure onto the VM. But it suffers much less than not having that feature, being forced to swap, and when you swap, your performance falls quite a bit more. So that's really what memory compression buys you in 4.1. Go through a couple quick troubleshooting tips here. It'll kind of cover the same areas that we talked about before. And we alluded to something that Scott talked about device latencies and device queues. So in general, when you're looking at ESX performance and you see device latencies cost certain thresholds, that's when you start looking at storage as possibly being the source of your problems. In general, if you see 15 milliseconds or more for your IOs, you probably need to start looking at storage as something that's contributing to your performance issues. Now, one thing to remember here is there are certain IOs that do take longer. If you're doing a backup, for example, and then you might be writing very large blocks, 128 or 256K blocks. Those do take longer to move around. I'm talking here about OLTP or regular file access type IOs, which tend to be in the 8 or 16K block size range. And if those are slowing down beyond 15 is where you want to react. Beyond 30, you definitely want to start looking at what your array is up to. You're probably overwhelming some LUN somewhere. Now, the other thing here is kernel latency. And we'll go into how to see each of these. So kernel latency is a measure of how long ESX has to hold on to an I/O before it can actually issue it to your storage device. So when does that happen? When your queues for the device itself are full. So you have a LUN. A single ESX host has 32 entries on it by default. You can increase it or decrease it, as the case may be. And there are but once that LUN queue is full, then ESX says, hey, that LUN queue is full. I'll hold on to this I/O for a little while and see if the LUN queue frees up. So the kernel latency is a measure of how long ESX had to hold on to that I/O. So how do you see these? So you can see them in vCenter or on ESX top. And on ESX top, you see a D average, device average, and a kernel average, and it reports both latencies. And over here, you can see it's 17.31 for the device, maybe worth looking at. Kernel average is starting to show up there. Not very large then, but even then, worth looking at why that's happening. The other thing that we added in ESX 4.1 was NFS latencies. Great, I see a few thumbs up here. So
yeah, we got a big round of applause last time we said that finally NFS stats existed for performance management.
So what we have now is we can actually report the latency that the guest OS is seeing from the NFS device. So we get this latency from the vSCSI layer. So we don't really have adapters or kernel queues in case of network storage. So all you can really report is what is the latency that the guest is seeing from that NFS volume.
So I'll also briefly mention a tool called vSCSI Stats, and then we will wrap up and allow a good 10 minutes for questions. vSCSI Stats, I hope that all of you have at least heard of, and if you haven't, write this name down and Google it. There is enough documentation to figure out how it works. vSCSI Stats, instead of averaging together IOs over a sample window, it actually records stats of every IO and puts them in a histogram. It does that by collecting them as is shown here. Let me zoom in on this. So consider this as a histogram. There are buckets, as there are on the right. This is a latency bucket, which means a certain number of IOs were either less than 1 microsecond at the top, then less than 10 microseconds but greater than 1, then less than 100 but greater than 10. And on the far left is the number of IOs that fit into that bucket. So I'll give you one example. This means 38,600 IOs came in faster than 15 milliseconds. Faster than 15 milliseconds, but slower than 5 milliseconds. Now, why is this useful? vSCSI Stats will find something that a professor of mine many years ago called the double humpback curve, where you've got a majority of IOs, a majority of any sample coming in at one bell curve, and a bunch of outliers that for some reason are coming in at a distant curve. That distant curve could be caused in storage by alignment issues or a non-persistent fabric problem or a variety of weird things that require people that really know what they're doing in the storage space. But you can observe them with vSCSI stats, and it can give you hints of what to look for. So as we're summing up, I want to say follow the best practices. I think that's probably not a surprise to everyone. I'll recommend those of you that want to ask questions, we're going to use the mics. So if you wouldn't mind, start walking to the mics now. Overcommit memory safely. As much experimentation as we've done, it seems that you can overcommit memory and you can protect memory performance by using reservations. Something I've been thinking a lot about lately is how you can develop an SLA against a VM by setting a certain size, test against that size, that's your maximum performance. Try setting limits to only half the size and test a second time. That will be your SLA, the half performance. Because when you go to production, what you should do is you should flip the limit to a reservation. So the half performance you test, you guarantee through reservations. That's a really great way to try to get an SLA. It's almost a performance guarantee. It's not quite, because if your network or your storage goes haywire, storage will suffer. But performance will suffer. But it will guarantee that you've got the performance you need out of your memory and CPU. Next, this troubleshooting guide is one of the most popular documents that performance engineering has ever written. A guy named Hal Rosenberg developed this about 40-page document that goes through a detailed flow out of how to correct every problem. Kaushik mentioned this is really not a troubleshooting performance class. There were 2 troubleshooting classes that you should watch recorded from Krishna, probably one of the most technical and best troubleshooting people in the company. Ravi gave one of the most popular talks, as he always does. He's extremely entertaining. And third, Chetan did some SIOC things. Those are all recorded. And that document encompasses everything that everyone does. It's got stuff on guests, on hosts, on storage, on memory, on CPU, best practices, everything. And here are a bunch of resources you can use offline if you guys have any interest at all in following what the performance community is doing. The white papers that we published are on the technology pages. Probably one of the most fun pages to read is the performance blog. There are regular updates there about every time some work is done. And I've got Twitter and blog stuff up there as well. I'll briefly say that everyone should please vote, kindly, I hope. But if not, at least vote, And I'll leave this up for those of you that want to see what to look at. Questions? I see we already have one person.
So if I have iSCSI and what do I use, NetIOC or Storage IOC?
If you're using iSCSI and the initiator is in the host, you'd be using Storage IO control.
Well,
if it's in the guest, you would be using NetIOC. But you want to give some advice on that, Kaushik?
So finally, you'll go through, iSCSI becomes a separate traffic type in your network IO control, so you can use both. Your storage IO control, you have multiple VMs from multiple hosts going to that one device, so storage IO control manages shares across those VMs. Network IO control basically ensures that it does not swamp the network card on that specific host, so you really need to use both.
Yes, sir. I think there's another one.
Is there any way of notifying an admin that storage IO control is working as opposed to just active?
Yes, absolutely. So I looked into this just before I left. In fact, I hope we can get some sort of a script together that will help with this. So there are new counters in storage IO control around normalized latency and around queue size. And both of those can be alerted off of. Unfortunately, the vSphere client by default does not include those counters in the GUI. So you can't go to the GUI and do drop-downs and set those alerts by yourself. But they are programmatically available through the APIs. So very, very easy. You can write tiny little scripts that will set alarms off of normalized throughput as well as a change in queue size. And that effectively will let you know that SIOC is now taking effect. I'll have to refer you to the SDK people, and I know there's a web page for that. My friend Pablo Roche can help you out if you need more help. So just contact me and I'll connect you to him.
Thank you very much.
Sure. Question from Chris.
Can you tell me if you think that the login consultant's paper for giving a one-to-one relationship between pCPUs and vCPUs for virtualizing XenApp workloads is still relevant?
Oh, boy, that's a good question. I think, so who made the recommendation that you should do a one vCPU to one pCPU?
There's a company called Login Consultants based in the Netherlands.
Oh, to hell with those guys. No, I'm joking. I know what you're talking about. So first off, I'll actually ask Kaushik to comment on proper sizing. But I don't think it's fair to say they gave a recommendation for that. For those of you that don't know Login Consultants, we have been struggling for a long time to produce a good desktop workload, and I think VMware has just now got something out that's absolutely fantastic. In that vacuum, Login Consultants and Project VRC did really what is really one of the only good analyses out there. We really wish they had added some more applications and some more operations. They're heavily focused on just a few operations that I don't personally think are realistic. But you got to give these guys credit. They just jumped in and did it on their own. I don't know that they recommended a one-to-one mapping, but that was the only way they tested for sure. Kaushik, why don't you give us some ideas about what you should see in terminal services consolidation?
So I don't completely understand the recommendation that you mentioned, but if they're basically saying, take your current farm, if you're running a 2 vCPU physical server, you automatically need a 2 vCPU virtual machine. And that I would disagree with, because you could be running on a much older piece of hardware. Most of customers today who are looking at virtualization have their applications already running, and it might be running on a 7000 series Xeon, for example. And if you're taking that and running this on an Nehalem now, I wouldn't give that a full CPU.
No, but his comment is if there are 16 cores, only having 16 vCPUs.
Oh, not overcommit.
No CPU overcommit.
Once again, the other thing that you have to consider here is I don't know whether you're taking hyperthreading into account or not. On the Nehalem, vSphere type CPUs, hyperthreading is significant. It does give you a significant boost in performance. So that is one thing to keep in mind. It depends on how busy your farm is, frankly. So if you are able to, let's say, geographically split your farm. So you have a few users in the US, you have users in Europe, you have users in Asia, and you have different peak times for each of those. You don't really want to share the VM itself, but you do want to share the host. You will be able to overcome it in those cases. If you expect that you have 8 2 vCPU VMs running on this 16-way host, and all 8 of them are going to be fairly busy, then yeah, it might not make sense to over-consolidate that further. You have to remember that Citrix itself, the Zen app itself is a consolidation environment, right? You're taking many users and putting them on a single area to work on. So that consolidation is already happening. So over-consolidating that may or may not make sense depending on whether you have those situations.
Yeah, it would be fair to say that since you're already consolidating the physical environment, that would be an environment that would be closer to 100% utilization. So I could probably buy that Zen app might be closer to an application that you can do no CPU overcommit. But that's not at all a deficiency in vSphere. That's just a choice about consolidation.
And for a Windows 2003 terminal server environment that's running 32-bit operating system in terms of memory configuration for each terminal server, what would you recommend?
So I think the question was if there's a terminal services 32-bit running on Windows Server 2003, what would we recommend? The simple answer for that is there was a talk last year that is available to all of this year's attendees. Let me just sum up a couple of the key points. We tried for a long time to produce these documents that were as confusing as valuable, that would list through all the things you want to do in a terminal services environment. Watch that little blinking network icon, go pay attention to virus scans, make sure it's not doing auto update. It was like this laundry list of things that really confused people as to what was important. The truth is there's probably about 3 things that are absolute musts. One of them is you have to have hardware assist, full hardware assist with memory management unit. Now, if you are in 3.5...
This is 4.1.
4.1. So then the hardware MMU should be used when the hardware is available.
Yeah, it depends really on the hardware type that you're using.
So you want to have an Intel Nehalem or sooner, 5500 or sooner, or an AMD Shanghai or sooner, which is now a couple of years old. The next thing is we've done a lot of work at looking at transparent page sharing. There's no problem with TPS that we know of with XenApp, right?
Yep.
Yeah, that is actually a false bit of guidance that somehow got onto the industry, that TPS was a problem, not an issue. Next is we just mentioned consolidation. So pay attention to what the utilization is in the guest. If it's near 100%, you're going to be doing one-to-one vCPUs to physical CPUs. If not, you can put more on there. The last bit of guidance I would give is, for most people, you actually probably want to stay away from the 64-bit version of XenApp and the 64-bit OS. Something I learned in my work at Intel was that when you take a 64-bit OS, like we were doing XP x64 at the time, and you run 32-bit apps in it, there's a penalty of the memory switching mode when you go from 32-bit to 64-bit that can actually slow down 32-bit apps. That's very much application dependent. So most XenApp customers are running these kind of legacy 32-bit apps. You want to stick with the 32-bit version of XenApp and scale out that farm with multiple XenApp instances on top of vSphere. Not go to the 64-bit one and run a whole bunch of desktops in one environment. That will hurt performance some.
Thank you.
No other questions? Okay, we'll hang around for at least a few more minutes. We got some time. Well, come on up if you don't mind. Thank you, everyone.